Okay, so if we're going to draw a card at random, right, from that deck, and we draw a card that is both an ace and a king, is that possible? Okay, so someone said, Jonathan said no. And Michael said no. And they're both right. You can't, right? You know, it's not like a trick or something. But okay, forget what I said. But there's no tried to make a joke, it didn't work. But there's no, but basically you cannot draw a card that is both an ace and a king. That's impossible. It's not like you're drawing a card that's a king of hearts. So that would be a king and a heart. So that tells you these events are mutually exclusive. In other words, let me get back to this. Stubborn, right? Here we go. Wait, let me make these bigger. So in other words, if A was the event, the first card is an ace. B is the event, the card is a king, right? A and B are mutually exclusive. As you can see here, the probability of A and B is 0. I mean, that's why they're mutually exclusive. Each one of those each one of those has probability 4. You know, there's 4 aces in the deck, and there's 4 kings in the deck. So the probability of A or B, as you can see here, is 8 out of 52. 8 out of 52. Again, this is 0. I mean, I really didn't have to write it, but I felt better doing it. All right. I hope that makes sense to everyone. I mean, I'm not done yet today, but I want to move on to the next part of this chapter, okay? Which has to do with counting. Now, you might be thinking, why do we have to worry about that? Well, we do actually need methods for counting and listing all the outcomes efficiently. Maybe not so much for listing the outcomes, although that would be beneficial, but really more for determining how many outcomes there are. Now, some of you are probably thinking, well, wait a minute, can't you just list them all? I mean, we did do that for some experiments already. You know, for the one where we tossed a two-sided coin and rolled the die, so we were able to list all those outcomes. The book actually does more. For instance, what they do is if you roll, they consider the experiment, if you roll a standard 6-sided die twice, they list all the outcomes. I mean, it's not terrible, it's 36, but what if we wanted to consider the experiment where we draw 2 cards from a deck of 52 cards? From a deck of 52 cards. You know, let's say we're not putting the first card back. Well, the first card, there's 52 possibilities. For the second card, there's 51. Well, I think we saw already, at least I told you already. Turns out there are over 2,000 possible outcomes. I don't know about you, but I do not have the patience to list all those outcomes. Okay? Or even if we roll the die 3 times, and each time we record the number. It turns out in that case, there are, yes, I just did it in my calculator, there's over 200 possible outcomes. So listing every outcome, I mean, yes, it's possible, but it's probably not the best way, it's probably not the best thing to do. I mean, there are ways we could efficiently list outcomes out, and that's what I'm going to show you first. But I really don't want to spend too much time on it. I mean, to me, what's more important is determining how many outcomes there are. That's actually pretty easy. It's just multiplying. But basically, let me do this one first. This is actually from the textbook, and it's illustrating how you can list the outcomes efficiently. I mean, you could use a table. That's what the book does. You can also, I can't speak. You can also make a tree. Essentially here, the example I'm doing is this. Suppose we're at a restaurant, and at the restaurant, you have different choices, okay? You can get an appetizer. There's 3 choices for that: soup, salad, or just breadsticks. There's 5 choices for the actual meal. I don't know what kind of restaurant this is. So there's hamburger, sandwich, quiche, fajita, and pizza. Hope I said that right, but I think I did. Let's suppose we can only choose one item from each category. So we can only choose one appetizer, and we can only choose one meal. How many different options do we have? Well, we can actually list them all. And it's probably better if we list them efficiently. That's what the tree here is helping us do. Basically here, okay, the way you make the tree is this. You have like a top where the branches come out from, okay? And for each, you have one branch for each of the first 5 outcomes, okay? So basically, we're considering the meal first. You don't have to, but that's what I'm doing. So we have a branch for each meal. We have the hamburger, sandwich, fajita, quiche, and pizza, okay? And then we consider the next category, so to say, the appetizer. Now there's 3 choices for that. So from each of these branches, as you can see, we would list these 3 outcomes. So from hamburger, we have these 3 branches. Same thing from sandwich. And we could keep doing this as I have over here. We could keep doing that. And then from this, from the tree, so to say, how do you get all the outcomes? Essentially, you're going to look at all the different branches at the bottom here. Right? So for instance, we have hamburger, then breadsticks. Right here is breadsticks. Okay? That would be one outcome. I mean, you could also get it. What I'm trying to illustrate down here is you start from the top and work your way to the bottom. So maybe it's not really a tree, I guess, so to say. It's really more, how do I say this? I guess upside down, because branches usually are higher up. But anyway, that's what we have here. Next, we have hamburger, and then soup. That would be another one. Then we have hamburger and salad. That's another one. And you do this for each meal option. And it does give you a way to efficiently list all the outcomes. These kinds of trees people do use when factoring numbers occur, what they call prime number factorization. So it's not like these are just in, probability. But from here, you can get all the possible outcomes. Essentially, it's how many branches there are down here. So what is it? That's 3, 6, 9, 12, 15 possible outcomes altogether. To list them, you would do what I just did before. You can also count them as well. 15 is not too bad either. So hopefully that one wasn't too bad. I mean, I don't remember if there's any examples where you have to draw a tree like this. Oh, we'll see. Now, as I said before, though, what's really more, this is important, but what's really more important is just knowing how many possible outcomes there are. And you can actually obtain that without drawing a tree or a table or anything like this. We have what's called the counting principle. Essentially, this is what they call the counting principle. Some sources call this the multiplication rule. The book says it's called the multiplication rule for probabilities. So, I mean, essentially, it's this. If you are asked to choose one item, okay, from 2 separate categories, okay, there are m items or m possibilities from the first category, and there are n items in the second category, so there's n possibilities in the second, the total number of available choices is m times n. Essentially, to get the total number of outcomes is you multiply. There are m possible outcomes for the first choice, and there are n possible outcomes for the second. You just multiply. That's what we're saying here. And here I'm actually just giving the idea about how to draw a tree. I mean, basically, we start out from the branch, right? And each branch you draw a branch for each item in the first category. So you would have m branches for each item in the first category, one for each item. Then from each of those branches, you're going to have n branches, one for each item in the second category. So here the first category is our meal. Hamburger, sandwich, fajita, quiche, pizza. For the second category, that's the appetizer, right? We have a branch for each item there. That's how we get m times n, 5 times 3 in this case, which is 15. And you could actually generalize this to more than just 2 categories. If there were 3, let's say, and there are m possible items or outcomes, let's say, from the first category, n possible items from the second, and w possible outcomes from the third, that's the third category, altogether then, there would be m times n times w. You just keep multiplying is what's happening. That's all. I mean, I wrote down the, how to draw the tree in that case. But the idea is really just, you just keep on multiplying. So that's really the idea. Let's see what time is it. We're doing good. I mean, that's what the counting principle is. And that's how I knew from the deck of cards we had, we had that over 2,000 possibilities, right? Because from the first card, right, our first category would be there are 52 cards to choose from. And after that card is selected, from the previous examples, there's only 51 cards left over. So in that case, you would have 52 times 51 possible outcomes. So you have 52 choices for the first outcome, because you have 52 cards. And you have 51 cards, 51 outcomes for the second choice. 52 times 51. I'm not saying you should draw a tree for that. That would be very tedious. This was the restaurant example, as I said before, there's 15 branches. This was with the die. If we were to roll 2 6-sided die, okay, then, record each pair of numbers that appear. I think I might have said this already. It turns out there are 36 outcomes, mostly because you have 6 possible outcomes for each roll. Well, I guess in the category idea, from the first category, right, that would be the number you can get from the first roll, 6 outcomes. When you roll the die the second time, right, going back to this, when you roll the die the second time, second category, there are 6 items to choose from, or 6 possible outcomes. Okay? And because of that, in total, there are 6 times 6, which are 36 possible outcomes. 6 outcomes for the first category, okay, which in this case is, rolling the die. And you're rolling the die a second time, so the 6 possible outcomes for the second category, hence there are 36 possible outcomes. Now, if you were to draw the tree, it would look like this. Although I didn't put in everything, but it would get a little complicated. All right. That's all I have for today. I'm not done with the chapter yet, but